It is now my pleasure to turn the webcast over to Dr. Peter Hurst, Executive Director, MIT Sloan Executive Education. Dr. Hurst, the floor is yours.
Thank you very much. Hello, everybody, and welcome to the next in our Innovation at Work webinar series from the MIT Sloan School of Management. We have over 1,400 people who've registered for today's seminar, so good morning, good afternoon, or perhaps even good evening to you, wherever you may be in the world. We're very pleased today to have with us Professor Tom Malone, who teaches in some of our Sloan Executive Education programs. And today we'll be continuing in our theme here of Innovation at Work, of bringing you the latest insights from world-renowned MIT Sloan faculty. And this webinar will be one in which Professor Malone presents some of his work and ideas, and at the end of the webinar we'll also have some opportunity for interactivity and for you to ask questions online in this system and in a Facebook chat coming up immediately afterwards. So it's really my pleasure to welcome Professor Tom Malone to the webinar. As you can see from the slide which has just come up, Professor Malone is really one of our most eminent faculty here at MIT. He really is someone who has been incredibly prolific in contributing breakthrough ideas in many fields of research that he's been engaged in. And we'll only be able to touch on a very few of those in the next hour or so. But you can see here in the bio just how extensive this work is. So it's really a great honor and a privilege and a pleasure to have Professor Malone with us. And I'd like to hand over now to Professor Malone, who is going to talk to us about how can we create more intelligent organizations.
Okay, thank you very much, Peter. It's a pleasure to be here today. As Peter just said, I want to talk today about how to create organizations that are not just more productive, but more intelligent. Now, to even think about that question, one of the first things we need to realize is that intelligence is not just something that happens inside individual brains. It also arises in groups of individuals. In fact, I define collective intelligence as groups of individuals acting collectively in ways that seem intelligent. Now, by that definition, collective intelligence has existed for a very long time. Armies, companies, countries, families, these are all examples of groups of people working together in ways that at least sometimes seem intelligent. But in the last few years, we've seen some very new kinds of collective intelligence enabled by the Internet. Think of Google, for instance, where millions of people create web pages, link those web pages to each other, and then all that knowledge is harvested by the Google algorithms, so that when you type a question in the Google search bar, the answers you get often seem amazingly intelligent. Or think of Wikipedia, where thousands of people all over the world have collectively created a very large and amazingly high-quality intellectual product with almost no centralized control, and by the way, in most cases, without even being paid. Now, I think these relatively early examples of new kinds of information technology-enabled collective intelligence are just the beginning of the story. I think we're likely to see lots more examples of these things over the coming decades. And if we want to try to predict what's going to happen, especially if we want to take advantage of these changes, we need to understand the possibilities for collective intelligence much more deeply than we do so far. That's our goal in the MIT Center for Collective Intelligence, and in a sense, that's my goal in our next hour here together. One way of framing the core question is this: how can people and computers be connected so that collectively they act more intelligently than any person or group or computer has ever done before. Now, to help answer that question, one thing that would be very useful is some way of measuring the collective intelligence of a group. So I'd like to tell you about a project we've done to do exactly that. We've used the same statistical techniques that are used in individual intelligence tests, but here we've applied those techniques to measuring the intelligence of groups. We found that just as for individuals, there's a single statistical factor for a group that predicts how well the group will perform on a very wide range of very different kinds of tasks. Now, it turns out that this factor, which we call collective intelligence, is moderately correlated with the average individual intelligence of the people in the groups, but only moderately. In other words, just having a bunch of smart people in a group doesn't necessarily make a smart group. Now, many of you already knew that from your own experience, but here's a very precise scientific demonstration of that fact. And of course, this also leads to another question, which is if just having a bunch of smart people doesn't make a smart group, what does? In this same research, we did find 3 other factors that are significantly correlated with the collective intelligence of a group. The first is the average social perceptiveness, or what you might call social intelligence of the group members. We measured this by giving people in the group a test called reading the mind in the eyes, where they see pictures of other people's eyes and then try to guess what emotion the person in the picture is feeling. When you have a bunch of people in a group who are good at that, then on average, the group is more collectively intelligent than when you don't. The second thing we found that was significantly correlated with the group's collective intelligence was the degree to which people participated about equally in the group conversation. If 1 or 2 people dominated the conversation, then on average, the group was less collectively intelligent than when the participation was more equal. Finally, we found that the group's collective intelligence was significantly correlated with the percentage of women in the group. More women was correlated with more intelligent groups. Now, it turns out that this last factor is mostly explained statistically by the first one. That is, it was known before our work that women on average score higher on this measure of social perceptiveness than men. So at least one possible interpretation of our results is that what you need for a group to be collectively intelligent may just be to have a number of people in the group who are good at this social perceptiveness or social intelligence. And if you have that, it may not matter much whether the people are men or women. But if you know nothing about a person besides their gender, you're a little more likely to get that with a woman than with a man. Now, some people think this is a sort of typical diversity result, but in fact, it's not the same as a standard diversity result. Standard diversity claim would be that the most intelligent groups would be those that are about half men and half women. But that's actually not what we found. We didn't design our study specifically to look at this, but the chart shown here shows that the relationship between the collective intelligence of the group and the proportion of women in the group is roughly linear. In other words, it seems to increase with more women, perhaps even almost all the way up to having all women in the group. Certainly the groups that are about half and half are, at least in our study, among the least collectively intelligent groups. So I don't think this is the definitive word on this, but I think these results are at least provide intriguing suggestions for how we should think about creating groups in our organizations today. Another result that I think is in some ways even more interesting comes from some more recent work we've done, where we've compared face-to-face and online groups. We had some groups taking our collective intelligence test sitting around a table talking to each other, and we had other groups taking the same test but not seeing each other at all and only being able to communicate by typing text messages to each other. What we found was that the social perceptiveness or social intelligence of the group members was almost exactly equal in those two cases. In other words, even groups who could not see each other at all, but which contained people who were good at reading emotions in eyes, those groups were just as collectively intelligent as face-to-face groups with those same abilities to read emotions in eyes. And the correlation was the same in the two conditions. What I think that means is that this test of reading emotions in eyes must actually be measuring a much broader set of interpersonal skills than the specific things it's testing. It must be the case that this test is also correlated with all kinds of other interpersonal and social skills people have, like the ability to guess what's going on in other people's minds, like the ability to know how other people are likely to respond if they say X rather than Y, etc. So one way of thinking about the implications of these results for work in organizations is that there are two important conclusions. One is that broad participation in decision-making can lead to more intelligent groups. The other is that interpersonal skills may be even more important than we thought in the electronically connected organizations of the future. In other words, there are two main factors that go into determining the collective intelligence of a group. The first is who's involved in the group in the first place. The second is how the people in the group work together. Now, it turns out that information technology can be important in shaping both of those factors. And that's what I want to talk about for the rest of our time together here today. I'd like to do that in the context of another project we did on what we call the genomes of collective intelligence. To do this, we first collected a number of case examples of different companies or other kinds of organizations doing things we thought were interesting examples of some kind of collective intelligence made possible by the Internet. So the examples we collected included things like Google and Wikipedia and Innocentive and the community that developed the Linux open source operating system and a number of other organizations like that. And what we found when we analyzed all these different stories, all these different case studies, what we found was that there was a set of patterns that came up over and over and over again in all these different examples. Different patterns in how they designed the interactions among people. Now, you could just call these things design patterns, but we like to use the word genes by analogy to biological genes as a kind of shorthand for these design patterns. In this work, we identified a starting set of about 18 of these genes or design patterns, the most important of which are shown on this diagram. Essentially, any activity or any organization needs genes to answer 4 questions. What is being done? Who is doing it? Why are they doing it? And how are they doing it? Now, to give you a sense of how these different genes fit together, let's think about the example of the community that developed the Linux open source operating system. For those of you who don't know the story, it started in 1991 when an undergraduate student named Linus Torvalds at the University of Helsinki wrote the kernel of a version of the Unix operating system to work on PCs. Nothing terribly unusual about an undergraduate computer science student writing software like that. But what happened next was extremely unusual. Linus Torvalds put the software he had developed up on the internet, which was at that time still fairly young, and he said to anyone in the world on the internet who wanted to, you're welcome to take this software, use it, change it, document it, do whatever you want with it. And a few people took him up on that, and then a few more, and a few more, and a few more, and eventually many thousands of people all over the world had extended his software, had documented it, had corrected errors, had made it far bigger, more capable, and more robust. And in fact, now the Linux operating system is one of the most important operating systems in the world. But it was developed by this very loose global community of software developers, none of whom actually worked for Linus Torvalds at all. It's the first major example of what we now call open source software development, a very interesting example of a new kind of collective intelligence, and one that happened and that worked through some combination of good intuition on the part of Linus Torvalds and also, I think, good luck. A question for us to think about, though, is how we might, in some sense, repeat that kind of success, how we might think more systematically about how to create new kinds of collective intelligence using the capabilities that are now widely available. And in some sense, that's what our structure, our framework about collective intelligence genomes is designed to do. To give you a sense of how it might work, let's do a kind of thought experiment and imagine what would have happened if Linus Torvalds had had access to the collective intelligence genome framework that's summarized, for instance, in our Sloan Management Review article, a reference for which is at the end of the slides, which you'll get a copy of. What if he had had access to that in 1991? So let's do our thought experiment by imagining there's some kind of time travel device that made it possible for Linus Torvalds to have access to this one article in 1991. If he had had that, how might he have been able to think more systematically about doing what he ended up actually doing with the Linux open source operating system community? Well, the first question he would have asked himself would be, what do I want to do? And in this case, the answer would have been he wanted to create new software modules. The next question he would need to ask himself is, okay, who is going to do that? Now, if Linus Torvalds had been a manager at a software development firm like Microsoft or IBM or something like that, the answer would have been, the people who work for me are going to do what I want them to do. But in this case, he was just an undergraduate college student. Nobody worked for him. So he made a very interesting choice in how he answered that who question. He said, anyone who wants to on the internet is going to create these new software modules. That's an example of what we call the crowd gene. The next question he would have asked himself is, well, why are these people going to create those software modules? Again, if he had been working for a company like Microsoft, the answer would have been because that's what they get paid their salary for. But in this case, nobody worked for him. He didn't have any money to hire anyone. So he couldn't appeal to what we call the money gene. Instead, he had to appeal to the other two why genes, what we call the love gene and the glory gene. In fact, if you read the email where he first announced the availability of this software, he wrote the whole message in a kind of playful tone like, gee, wouldn't it be fun if we could all developed this operating system to do all these cool things on PCs. In a sense, he was very clearly appealing to the love gene of all the people who he wanted to motivate to write these software modules. The last question he would have had to ask himself is how. In this case, what he would have needed to do is have different people developing different modules which are actually interdependent among themselves, and that's an example of what we call the collaboration gene. So he's now answered all 4 questions, but if you think about it, he's not really through. Because what he's saying is, well, we want anyone who wants to on the internet to create new software modules for love and glory, collaborating with each other all over the world. But how do we know that the software modules they're going to be creating are any good? How do we know that they won't be full of bugs? And how do we know that the modules that somebody on one side of the world creates will actually work with the ones created by people on the other side of the world? So what Linus Torvalds would realize next is that he actually needs to ask all 4 questions again for another part of the problem, which is how to decide which of the software modules people send in will actually be included in the next version of the software that's released. In fact, it's quite common when you are creating things to have not only a set of create genes, but also a set of decide genes. In this case, Linus Torvalds could have done something kind of radical and innovative, he could have said, well, we'll let everybody vote on which modules should be included and which won't, but he didn't do that. Instead, he used a much more conventional approach for this part of the problem. He said, I'll decide which of the modules get sent in will be included, and when that gets to be too much work for me, I'll ask some of my friends to help. Again, nobody's going to pay them for this, so they're motivated by love and glory, but here they're using a more traditional hierarchical approach to solving this problem of how to make the decisions, not just how to create the software modules. So if you look at the slide here, what's summarized on this slide is essentially the genome, the set of genes in the genome for the community that developed the Linux open source operating system. And that gives you a sense then of how these genes can fit together and how you can use this framework as a way of deciding or actually inventing new kinds of organizations, new kinds of collective intelligence. Now, a lot of the action in this framework is in the how genes, a number of which are shown on this slide. We don't have time today to talk about all of these, but I'd like to give you just a taste of what the framework is like by talking about 2 of these genes, the gene we call hyperspecialization and the one for what we call prediction markets. Let's start with the hyperspecialization gene. This is a subtype of what we call the collaboration gene, but it's one where the things that individual people do are much smaller and more specialized parts of the overall process than is typical in today's jobs. Now, we're actually familiar with this concept of division of labor because it's very common in factories. In fact, if you think of Adam Smith's pen factory several hundred years ago, that was a place where what used to be the job of a single person, a pen maker, a craftsman called pen maker, what used to be the job of that one person was broken up into much more specialized jobs for people doing smaller parts of the overall process, but each one was doing only that small part. For instance, one person in the factory would cut the wire. Another person would put a point on the pen. Another person would shape the heads that were to go on the pens, etc. And by breaking this job that used to be one person's job into 20 smaller jobs, they were able to get huge increases in productivity, the benefits of which we're all familiar with from our industrial society. But that kind of division of labor has mostly been done so far for physical tasks. I think we're about to see far more of that in the coming decades for informational tasks. Because new information technologies reduce the costs of communications so low, it's now possible for people all over the world to communicate almost free and almost instantly almost any kind of information. What that means is that we can now, in principle, move information work anywhere in the world relatively easily, and therefore get global economies of scale for people doing even very small parts of an overall information process. So that's what I call hyper-specialization. Let me give you some examples of that to give you a sense of how it can work. First example I'd like to use is a system called TopCoder. This is a software development platform now owned by Apereo Incorporated that includes a community of over 600,000 freelance programmers all over the world. The way TopCoder develops software is by breaking the overall process of software development down into smaller pieces than is usually done. For instance, they have different tasks like specifying the requirements, designing the overall architecture, programming different modules like user interface modules and so forth, putting them all together, etc. Different freelance programmers all over the world compete to do these tasks, and importantly, different programmers specialize in doing different kinds of tasks. For instance, there might be one programmer in Poland who spends all his time on the system writing software for user interface modules for the Apple iPhone. There might be somebody else in India who spends all of her time debugging software written in Java. And different people in different places could focus on different things and get very, very good at the specialized tasks they did, and they could use their highly developed skills as part of much bigger projects that also included other people all over the world. By doing that, TopCoder is often able to develop software much more quickly and at lower cost than more traditional software development methodologies. An even more extreme example of hyper-specialization comes into play with the system that Amazon has called Mechanical Turk. Now, let's talk first for a minute about where that name came from. It turned out there was a sensation in the 18th century in the royal courts of Europe because there was this chess-playing machine called the Mechanical Turk. The picture there shows what this machine looked like, a kind of robotic-like Turk who played chess, and this machine was carried from court to court in Europe, and in each country, some of the best chess players in the country would come and play against this chess-playing machine, and they would almost always lose. So this was a great sensation. People thought it was quite amazing that a machine could do that. It was later revealed, however, to have been a hoax. In fact, inside that box, a very small but very good human chess player was hiding and controlling what was said to be the robot. And the box was cleverly designed so that when they opened up the door, as is shown in the picture, to prove to the audience that there was no one inside, the little man could scurry from one side of the box to another and people would never see him. So that's an example of what you might think of as artificial intelligence. In other words, it was a person pretending to be a computer doing intelligent things. And that's essentially what Amazon's Mechanical Turk is. It's a framework, in some sense it's an online labor market through which you can hire people to do very small tasks called micro tasks. You can even have them do that as part of an overall computer program, and the people do the things that the computer can't do itself, that are hard for computers to do, or you can just do that as a separate human-controlled process all the way. But people use this for a number of different things. It was originally designed by Amazon to get people to help them do copy editing and other maintenance on their own web pages describing their Amazon products. But they made it available for other people for all kinds of other tasks, like people sometimes use it to transcribe speeches or talks or meetings where you can have different people each transcribing a couple of minutes of a talk, and then you just put all those transcript segments together into an overall transcript of the whole audio. Or you could have people read a news article that you think might be about board membership of a company, and the person can just answer the question whether this article describes someone leaving or joining a board. Interestingly, many of these tasks are very small, can be done in only a couple of minutes often, and they also pay only a few cents. Now, to give you a sense of what's possible with this mechanical Turk system, I'm going to describe another system developed by some researchers, colleagues of mine who are at Carnegie Mellon University. They developed a system called Crowdforge, where crowds write documents using the Amazon Mechanical Turk framework. For instance, one of the examples they've spent the most time on is writing an encyclopedia article about New York City. The way they do this is kind of analogous to how TopCoder works with software, but here they're doing it with just developing text documents, in this case an encyclopedia article. They start the process by having one group of Mechanical Turk workers come up with outlines for a possible encyclopedia article about New York City. And then each of those outlines is sent to another group of Mechanical Turk workers who rate the quality of the outlines they look at. The outline that gets the highest quality rating in that process is chosen as the basis for the next step, where for each of the sections in that outline, they send out the name of the section to a number of Mechanical Turk workers and ask them to generate facts that are relevant to that section. For instance, the second row of the slide here shows some facts that are relevant to the section on attractions in New York City. Again, each of those facts is rated by other workers, and the most highly rated facts for a given section are put together and sent out to another set of Mechanical Turk workers who are asked to write a coherent paragraph using the facts that are shown here. Again, those paragraphs are rated by other Mechanical Turk workers, and the most highly rated paragraph for each section is put together with all the other highly rated paragraphs for the other sections to make a completed encyclopedia article. Interestingly, when they show these articles to independent judges, they say that the articles written in this way are better than similar articles written by a single individual who wrote the whole article for the same cost. And they're roughly equivalent to the simple English version of Wikipedia articles on the same topics. So I think this is an interesting example of what you might think of as industrial writing. And I think it suggests the way much more writing may be done in the future. If you think about it today for physical products like furniture and clothing, we nearly always use versions of those products produced through an industrial process, essentially a factory. But we do occasionally have handmade clothing or handmade furniture. I think something similar may happen with writing in the future. That is, it may become the case that most of the writing we see is written in some kind of industrialized process like this, and that we will occasionally see things written by a single individual, but those may be as rare in the world of the future as handmade clothing and handmade furniture is in the world of today. So that's a provocative possibility for what hyper-specialization may lead to. The other gene I'd like to talk about is the prediction markets gene. This is a way of using what you might call the wisdom of a crowd to make predictions about the future. One of the first cases in which this approach was used in business was some years ago when Hewlett-Packard used it to predict sales of their printers. The way it works is that participants buy and sell predictions about uncertain future events. For instance, if you thought that the specific printers they were predicting would sell somewhere between 1,500 and 1,600 units in the month of September, you could buy a share, or in fact as many shares as you wanted, of that prediction. And if you were correct when the sales figures were actually known for September, you'd get $1 for every share you owned of that prediction. If you were wrong, you'd get nothing. So if you think about it, what you should be willing to pay for one of those shares is essentially your probability estimate of that event actually happening. For instance, if you thought there was a 65% chance that the shares would be in that range, you should be willing to pay anything up to 65 cents for one of those shares, and you should be willing to sell one for anything more than 65 cents. So in a sense, this is a way of collecting a bunch of different people's probability estimates for these future events. But it's a way of doing that in a very interactive way where people are actually have financial motivations to buy and sell the predictions on the basis of their actual beliefs. What happened when Hewlett-Packard did this was they let people trade in this market for several days. They looked at the predictions that came out of that, and it turned out that those predictions were more accurate than the official Hewlett-Packard sales forecasts at the same time. In fact, this result is not at all uncommon. People have used prediction markets to predict all kinds of things, from product sales to movie box office receipts to who will win presidential or other elections. And these prediction markets are often more accurate than other methods we have for predicting those things. For instance, here's a graph showing a prediction market for who will win the next U.S. presidential election. It shows the prices in that market over the last 2 years. The red line there represents Hillary Clinton. The turquoise line represents Jeb Bush, and the others are below that. As you can see, the current prediction as of a few days ago that Hillary Clinton will win is about 60% chance. Of course, that doesn't mean that she will necessarily win. There's a 40% chance, according to this, based on what's known today, that she won't win. But it does show that her predicted probability is quite a bit higher than any of the other current candidates. So this is an interesting way, I think, of pooling lots of people's judgments and also giving people motivations to incorporate any new information that's available very rapidly into their predictions. For instance, you can see a little over a year ago, there was a period where one of the other candidates, in that case the gray line is Ted Cruz, for a brief period, right after he made some speeches in Congress, I believe, was very close in the market's prediction to Hillary Clinton, but then they diverged soon after that. To take this notion of prediction markets even further, let me tell you one other example of how prediction markets have been used in business. Several years ago, Microsoft used some prediction markets to predict the release dates for internal products. And at the time they opened these prediction markets in August, there was a product that was scheduled to be released in November. The manager of the group developing the product thought things were pretty much on track for November release. But when they opened the prediction market, within the first 2 minutes of trading, the predicted probability of on-time release of this product went down to about 2%. In other words, there were lots of people participating in this market who thought there was no way the product was going to be released on schedule. When the manager of the group heard this, he asked some more questions. He found out some things he didn't know. He made some changes in what the group was doing, and the product eventually was released in February. So here's a case where the knowledge about the problems with that product were actually widely known, the knowledge was widely distributed within the organization, but wasn't available to the manager who could have done something about it. So in this case, the prediction market made that knowledge more visible and more available in a way that people could actually act on. To take this notion of prediction markets even further, let me tell you about another project we're doing at MIT on what we call collective prediction, where we're combining people and computers to make predictions. We wanted to develop a method that could be used for predicting things like what a terrorist would do, or what an enemy would do in wartime, or what a business competitor would do in business. But we wanted a simpler and more sanitized example to use for our experimental purposes. So we picked trying to predict the problem of what would be the next play in an American football game, whether the next play would be a run or a pass. The way we did this was to show people videos of an American football game, stop the video just before a play began, and then ask them to predict whether the next play would be a run or a pass by buying and selling shares in a prediction market, an online prediction market. We also had a group of computer agents who were doing the same thing. They were also making predictions about whether the next play in the game would be a run or a pass based on a set of simple information they had about the game status, like what yard line the ball was on and how many yards to the next first down. The agents made their predictions and bought and sold prediction shares in an online market with other computer agents. And then finally we had a third set of prediction markets where people and computers were both participating in the same markets. What we found was that the prediction markets that combined both people and computers were both more accurate and more robust to various kinds of errors than the ones that had only people or only computers. Now that doesn't prove that you should always have a combination of people and computers. In some cases one or the other is much better. But it does say that there are at least some cases, and I suspect a fair number of cases, where the best results we can get will be from combining what people can do well with what computers can do well. The last example I'd like to tell you about is another project we're doing at MIT that actually combines many of the genes we've just talked about and a number of others as well. It's a project called the Climate Colab. And it's a project where we're essentially crowdsourcing the problem of what to do about global climate change. We have an online community of now over 36,000 people from all over the world, including some of the world's leading experts on the science and policy of climate change, but also including people from all walks of life, scientists, policymakers, business people, students, all kinds of people from literally all over the world. And together, this community of people is developing and evaluating proposals for what we can do about different aspects of the climate change problem. Those proposals, like the one shown here, can include any suggestions people have for technological or economic or social or other kinds of changes we might make. The example shown here is a proposal that won our grand prize a couple of years ago. It's about a way of using infrared photography from airplanes to show visually how much wasted heat is escaping from buildings on the ground. So for instance, homeowners can use it to see how much heat their home is wasting and compare that to the wasted heat from their neighbors' homes on a kind of Google Maps-like display. So in order to do this, we ended up breaking the overall problem, which is of course a very big, complicated problem of what to do about global climate change, into a number of more focused sub-problems on things like how to generate electricity with fewer emissions, how to adapt to rising sea level, how to change cultural attitudes about climate change. And in each of these different areas, we had a separate contest with expert judges and advisors who were selecting the winners from the ideas that all the people in our global community sent in. That's led to some very interesting ideas, but if you think about it, there's something else also needed. Once you've broken the problem down into pieces like that, you also need some way of putting the pieces back together. So this year, for the first time on a large scale, we're having a set of integrated contests where people put together integrated proposals, or basically climate action plans, at the regional and global level. And these climate action plans bring together ideas from all the other contests and potentially all the other proposals on the Climate Colab site into integrated ways of approaching climate change at the national and global levels. So in summary, I think the kinds of questions we need to ask are, how can we measure collective intelligence more effectively wherever it occurs? How can we design new forms of collective intelligence using new kinds of information technology? And how can we put both of these things together to create more intelligent organizations? Now, if we can do that, what's it likely to lead to in the long run? Before we end, I'd like to just give you one more thought about what the long-term future may look like. I think as our world becomes more and more closely connected through all kinds of electronic communication, it will become more and more useful to view all the people and computers on our planet as part of a single global brain. And perhaps our future as a species will depend on how well we're able to use our global collective intelligence to make choices that are not just smart, but also wise. Thank you all very much.
Thank you very much, Tom. That was a lot of very provocative ideas in there, and been having some questions coming in. I'd like to encourage everybody listening to keep asking questions through the website. I'll try to get to as many as we can. But maybe just to get started, going back to some of the things you were talking about at the beginning of the presentation, some folk were asking about the collective intelligence group project that you did.
Yes.
And we're very curious about what were some of the other factors that might have affected those results. Did you look at whether people had established sort of relationships with each other and knew each other, or perhaps were there any kind of cultural effects that you might expect to see in that?
Okay, good question. Some people think that those results might have been a result of using MIT undergraduates as our subjects, and it's important to say that was not the case. Who knows what we might have found if we had used MIT undergraduates. But the studies were done with strangers from the general public in the Boston and Pittsburgh areas. So we recruited using things like Craigslist and other things like that. People came into our laboratory and worked together with other people in groups of 2 to 5 people. They did not know each other before. They had no prior relationship, no particular expertise that we kind of assigned in any systematic way. So in that sense, these are artificial groups, not natural groups. In other words, in a real company, you would typically have people who work together for a long period of time. The people in the group would have been chosen for a certain combination of skills that were needed. So we don't know for sure that these results would apply in more natural groups as opposed to more to these artificial ones. But we do have a number of indications that they probably will, and certainly that would be my guess. One more recent study we've done, for instance, uses a different kind of group that is in some sense a natural group, and that is teams that play the online video game called League of Legends. So these are not work groups in the ordinary sense of work, but they actually do an interesting kind of work, battling monsters and other challenges in this online world. And we found that the teams that were most successful in the online game were also the ones that had the highest collective intelligence as measured by our test. We've also done some other work in other countries, including both Japan and Germany, where we gave people their translated versions of our test, and in both of those cases, the same general results were also replicated.
Does this give you any special insights into how companies should be trying to create high-performance teams? Are there anything about the composition of those teams or the systems, the work systems that they put them into?
Yeah. Well, I think perhaps the most important implication of this is that we should think about groups as groups, and we should think about measuring groups as groups, not just measuring the individuals in those groups. What we have done now in this work is develop an approach to measuring the effectiveness of a group as a group, not just the individuals in that group. As we saw, just having a bunch of smart people doesn't necessarily make the group smart. This is now a systematic way of measuring what does make a group smart. And we think one interesting possible is to use this in organizations to do some systematic assessment of that. You don't have to just guess who would be good working together. You can actually measure it. And in fact, one of the nice things about this is that to the degree this score on this collective intelligence test actually does predict other kinds of performance, as we think it will. And by the way, we're interested in finding companies that would like to have studies done to test whether this actually happens. To the degree that is true, it means you can do all kinds of systematic experiments much more easily with this test than you could with the real work being done. For instance, if you suspect that having a certain combination of skills or personalities in a particular kind of sales team is good, you could actually try that with the collective intelligence test and see if, in fact, it does lead to more collectively intelligent groups much more cheaply and easily and quickly than you could afford to do year-long tests with a real sales team actually selling stuff.
There's some very actionable ideas for people in that. I think we'd love to hear about anybody who's trying anything out like that.
Or would like to try something like that. Right.
Turning now perhaps to the question of collective work, and in particular you were talking about the idea of the industrialization of knowledge work. A couple of themes that are coming out in the questions. One is that, so we understand that enabling armies of people to do this work for you could perhaps have either quality improvements or cost reduction benefits. Yet there's presumably still some very special kind of highly valued person, individual, that knows how to set up and run these kind of collective work systems. Is that a valid assumption, or in fact is there a collective intelligence approach that you can use to designing and running collective work systems? Or in fact are we saying we really are going to create a very special kind of knowledge worker who knows how to set up organizations that can take advantage of these ways of working?
Yeah, so let me break that question into several different parts and answer each one. The first thing to say is that when you specialize work, and especially when you hyper-specialize work, a lot of people are doing a lot of small pieces of the task. But as we talked about there at the end with the Climate Colab, when you break a problem into pieces, you have to somehow put the pieces back together. Sometimes the very nature of the work makes it quite easy to do that. If it's just a matter of putting them next to each other and that's it, that's easy. But usually more work and more thinking is needed to reintegrate the pieces. So in many cases, a very important kind of hyper-specialized worker is a worker who specializes in integrating the work of other workers. In other words, a kind of generalist whose job is to coordinate or integrate, or in fact in today's world we often call that kind of work management. So that's an important kind of specialized work that will still be needed in the operation of many of these crowd-based systems. And that's in the actual operation of it. A second question is, how do we design these systems in the first place? And certainly some way of designing them is needed. They don't happen just magically. And I think in many cases, the design of these systems is the result of work by a relatively small number of people who design and kind of implement the system, whether it's Linux or Wikipedia or whatever it is. The question you asked may have been asking, could that also be done by a very large group of people? Could you have a very large self-organizing group? I think the answer to that is quite possibly yes. To some degree, Wikipedia is surprisingly self-organizing. There are some special purposes, special roles that are done by people called administrators and stewards in the Wikipedia community. But to a very large degree, the way the system works and the way the norms of the community work resulted from very decentralized decisions of many people in the whole community.
That's interesting. We're just about coming up to the top of the hour, and I know we're going to continue with the Facebook chat afterwards, but perhaps we've got time for one more question before I wrap up this section. Unless we've got several people who are particularly interested, this is the Innovation at Work webinar series, and we're at MIT. Do you have any quick thoughts or suggestions for people who are really interested in how these ideas could help them and their organizations be more innovative or drive innovation?
Well, as I said early in my talk, I didn't nearly have time to talk about all the things we've written about this today. I believe at the slide, in fact, here are a couple of slides that should be showing on the screen right now that give some further reading about the things we talked about. In particular, the second reading here on the collective intelligence genome goes into much more detail about the different design patterns or genes and how they can be used not only to help organizations be more innovative, but to do many other useful kinds of things. Some more reading is on these two slides as well. So those are two ways. There's much more reading on our website for the MIT Center for Collective Intelligence.
Right, and I think there's more information about the Climate Colab on your website as well, which some people were asking about.
Yes, the Climate Colab is just www.climatecolab.org.
That's great. I'm sure you'll get some more people looking at that. And perhaps if we just go to, I think, the next slide for some further insights and depth on this topic and to get into some more of the questions. We have a program coming up which is available online, so many of you around the world have the option of actually spending more time in that program hearing from Tom and actually working in groups, perhaps actually practicing some collective intelligence during that program. So it remains for me to thank Professor Tom Malone very much for this fascinating webinar. And thank him again for sticking around for the next segment, which is a Facebook chat. We're just going to put up the link in a second for that. We hope you can all join us for that. Thank you all for attending, and we hope many of you will stick around to engage in the next stage of this. Thank you, Tom, very much.
Thank you.
Thank you again for joining us today. This